People often ask me how a chemical engineer like myself ever got involved in clinical research, because it's kind of rare. I was in graduate school, building equipment, analyzing data, running experiments, and not exactly the traditional start to a medical career. So it turns out that it took about 5 years to get a PhD. And I was now an expert in the field of nonlinear dynamics and complex rhythmic systems. Now, I challenge any of you to find that phrase on a job advertisement. Needless to say, I was a bit concerned. Fortunately, there is a type of system, a rather important system, that exhibits complex behaviors, generates an awful lot of data, and there's a relatively large amount of grant funding associated to study it. You. And so I was offered a position in a medical center, which led me to my current position at Texas Children's Hospital. And so what I do is I look at new ways of analyzing data, specifically physiological data that comes over your bedside monitors in an intensive care unit. So what I learned in my lab is that the data that you can see is only a small fraction of the information that's actually available to you if you know how to look under the surface. And so my goal is to use mathematical tools to extract hidden information from within patient data and present it to doctors in an intuitive way so that they can better treat their patients. Now, this is called clinical decision support. So what do we mean by this? Well, decision support is, in order to understand it, we have to first understand what it's like for a doctor to treat a critically ill patient. And so let me tell you how I think about it. And because I'm an engineer, I'm going to use a car analogy. Treating a critically ill patient is a bit like driving a car in a city where all the roads are constantly under construction. Which might be hard to imagine here in Houston, but please bear with me. You see, when you're treating a patient, you know where you are, your current location. You know where you want to go. But getting to your destination may be tricky. Sometimes you can encounter obstacles. Sometimes the signs are just a little bit confusing. And even if you've been down a particular road before, you may wind up someplace that you didn't expect to. But thank God we have GPS. And this is a great decision support system because your GPS tells you where you want to go, and as decisions come up, you are prompted with a timely and accurate recommendation. It tells you where you go, where you want to go, what you want to avoid, and how you want to get there. And as a result, you can make better decisions as you drive. Or if you're a doctor, as you treat your patient. But imagine if you didn't have these fancy maps or the automatic traffic avoidance system or the rerouting. Imagine if your GPS device only told you your current position. It would look something like this. Now, such a device wouldn't nearly be as useful to you because the functionality that relates this data to the decisions you have to make when you're driving are no longer there. And in a similar way, the same situation exists in medicine. This is how a physician will navigate caring for their patient, using physiological data like heart rate, respiration rate, blood pressure, and blood oxygen saturation. But these are just coordinates. What's lacking is the device that takes these coordinates and translates it into a clinically relevant metric. And as a result, clinical staff has to constantly monitor these numbers in order to anticipate whether something's going wrong and then act in order to fix it. And the problem is that this is a huge challenge because there's an awful lot of data being generated. A typical ICU patient will generate between 100 and 200 megabytes of data per day. Now, to put that in perspective, if you are hospitalized for 5 days, you will have generated an amount of data equivalent your entire genome. And this is a great picture of a printout of what your genome looks like. So this is 5 days worth of your data. Now, if you're an institution the size of Texas Children's Hospital, you will generate approximately 100 terabytes of this data each year, almost half the size of the Library of Congress. How can we possibly expect our doctors and nurses to manually sift through this data, especially given the time-critical nature of the decisions they have to make and their impact on our outcomes? In order to answer this question, we need to reassess the way we think about monitoring critically ill patients. And that's where I come in. So I'm an engineer, and I work with the doctors at Texas Children's Hospital to answer this question. And we do this by combining medicine, mathematics, and engineering. Medicine grounds our team in clinically relevant questions. Math shows us new ways to analyze data and tailor it to specific diseases. And engineering pulls all the pieces together, allowing us to advance clinical care through real-time decision support. So instead of just providing coordinates to doctors, my team and I add the clinical context to patient data. And we do this by developing algorithms. And these are simply programs that can be run on a computer. And each algorithm is specifically designed for a specific condition and disease. So one algorithm might look for signs of pneumonia, another one for cardiac arrest, and yet another one for adequate brain perfusion. And using supercomputers, we can run thousands of these algorithms in parallel, providing continuous guidance to physicians that's customized for each patient in a hospital, because each patient is different. So my team and I are focused on blood pressure management for head trauma patients. So imagine if your child fell and hit their head and had to be rushed to the emergency room unconscious. Probably every parent's worst nightmare. From the time your child is admitted to the time that they're discharged, a number of critical decisions will have to be made, each of which can have a significant effect on their outcome. Now, one of these decisions is blood pressure management. And this is important because blood pressure is one of the key factors that will influence how much blood is flowing to your child's brain. And having adequate blood flow to the brain is critical for minimizing injury. But it's complicated. Too little flow, and you risk stroke. Too much flow, and you risk severe neurological injury. And so the question, to even make it more complicated, these things can change over time. So what's good for you now may cause harm 24 hours from now. And so what the doctor has to do is they have to continuously ask the question, do I increase, decrease, or maintain the blood pressure of this patient right now? And to help him answer this question, and he uses traditional patient monitoring. And so what he's doing is he's looking at these waveforms and numbers and trying to uncover hidden information buried deep within this data to give him an advantage, to tell him whether or not the blood pressure that is currently applied to this patient is adequate and is going to provide the best outcome. But the problem is that in order to do this, he would have to sit at this monitor for a number of hours and execute some rather complicated mathematical functions. But this is what computers are good at, right? So instead of having the doctor continuously watching this monitor, we can put a computer behind the curtain to continuously process this data to determine whether or not the current blood pressure is optimum right now. And then we can track that over time so we can maintain consistently optimum values. So the question for the engineers on the team is, how do we build such a monitor to help support this decision? Well, my team and I do this by first trying to understand the physiology of the problem. And in this case, we're in luck, because the brain has developed a mechanism that automatically buffers itself from extremes in blood flow. Vessels will expand and contract in order to maintain a constant flow rate. And so what we can do is we can go back in this data and look for signs that that mechanism is engaged. Because if it is, then we don't have to worry about it. The brain will take care of itself. And if it's not, then we have to make a change in order to make the brain engage that mechanism. And so to do this, we need to record patient data. And this sounds easy, but it's actually quite difficult. You see, for a given patient, it can be monitored by a number of pieces of equipment, each made by a different manufacturer, and each recording data in a different way. Oftentimes, this data is noisy, much like you'd hear static over a radio channel. You can't understand anything. We hit the same situation, and this data has to be thrown out. And in fact, in a data set of over 680,000 hours of patient data, we've shown that almost 30% of it is so noisy that we can't use it for analysis. Even more complicated is that patients tend to move between different beds. And sometimes their monitoring equipment moves with them, sometimes it doesn't. And it can be extremely challenging to identify a piece of information recorded in a particular bed with its former occupant. And on top of all of this, we have to protect patient confidentiality and code all of this data so that no researcher can trace it back to an individual patient. So overcoming all of these obstacles and going back into this data and looking for these mechanisms, we can develop an algorithm that identifies these patterns. In doing this, we can then go back and look at what the outcomes of patients were relative to what we thought how their blood pressure should be managed. And a group in Cambridge did this for the two most severe outcomes of head trauma patients, mortality in red and severe neurological injury in blue. Now, we have the basis for building a new type of monitor. See, if we run an algorithm on our patient and determine that their blood pressure should be somewhere around here, then we know that that area or that range is associated with the best outcomes for patients in this condition. So let's color that range in green, because this is where we want to be. Now, let's color all the other blood pressure values in red, because each of these is associated with a higher instance of mortality and injury. Now, if this monitor was running on your child, we would also need markers that delineate the line between good and poor outcome, as well as the current blood pressure. Now let's take this monitor, rotate it, and compare it to the traditional monitor. What we have here are two monitors that use exactly the same data. But this new monitor directly relates the physiological data of the patient to the most probable outcome as seen by other patients with similar injuries. It not only tells us where the patient is, but what direction the blood pressure has to go in order to receive the best outcome at any given time. And this is the idea behind clinical decision support. So decision support has the potential to change medicine in a fundamental and unexpected way, not by designing some new drug or medical procedure, but by amplifying the effectiveness of our existing hospital systems. And it's not a new idea. Almost 50 years ago, you could have seen such a monitor in Star Trek, the original series. Science is finally catching up to science fiction. Now, my team and I want to see decision support technology in hospitals across the country, and not just research hospitals, but medical centers, ambulatory centers, and doctors' offices. We want to bring the best medical knowledge to the bedside of every patient everywhere. Researchers are cracking the code for new diseases and new conditions using mathematical skill and clinical insight. Engineers are building new types of supercomputers that can process physiological data in real time and provide guidance to physicians. But to integrate this technology into hospitals will require us to foster collaboration between fields. Because when engineers, mathematicians, and doctors come together and resonate, the result is the next generation of medicine. Thank you.